at a distinct disadvantage, with the majority of the audience probably knowing far more about emergence than I do. I'm not only talking about the speakers today, but also about the students who, from my experience of going to crits, are pretty well immersed in emergence already. What I've learned about emergence, as Mike's already said, has really been through just the experience of putting together the issue with Mike, Michael and Achim. This is where I get the opportunity to plug the issue, and I'll get that out of the way. In fact, the emergence issue of AD is going to be published in just over a week, and you've all got leaflets on your chairs, signposting you down to the Triangle Bookshop, where I think that Derek sorted out a special price for you, so just another week. But so rather than compete at the level of the other speakers here today, I'm, if you like, going to take a few steps back. Talking from the position as an editor, and editors tend to know very little about an awful lot in architecture, I'm going to try and answer some really basic questions about emergence. Why emergence? Why have we bothered to devote a whole issue of AD to emergence? And why emergence now, at this particular time? Emergence isn't a totally new concept for architecture. And when I say new, it has been kicking up its heels in Columbia circles for well over a decade. We've just produced a revised edition of Folding, and in that, Greg Lynn describes the moment in the early 80s when architects first discovered calculus, the digital, and the scientific models of emergence, chaos, and complexity. And it's quite interesting that at that point, those were all bundled together in one go. And he referred to this to the most provocative and incoherent moments in architectural experimentation. The fact that the potential of emergence was first recognized by architects as a scientific model at the same time as the digital leap was made is probably not wholly incidental. It does, however, mean that for a few years, emergence's place in architectural thinking remained, if not incoherent, nascent and undeveloped. Emergence was, for much of the 90s, little more than a tantalizing concept that was circulated in a loose rag bag of architectural ideas. So, despite the immediate lack of direction, there was a strong sense of a cultural fit, if you like, between emergence and new developments in architecture. This was incited by the paradigm shift that came about with the onset of digital technologies. A strong analogy can be set up between the way that digital systems encourage us to work and the workings of natural, evolutionary systems. Both are widely thought of as bottom-up in character. This contrasts markedly with the conventional, deterministic modern model of practice that is top-down, where architects almost work backwards to produce a finite object through a linear process of concept sketches, models, and production drawings. So, digital processes have brought them with a new elasticity that invites repetition and reiteration. Is this room for variation and experimentation that has made the predetermination of form from the outset far less desirable? At the same time, the very reiterative nature of digital design, with its constant toing and froing and ceaseless recasting of form and structures, has also made editing a prerequisite. What better model for selection is there than emergence or morphogenetic design strategies which occur in the natural world, with evolutionary optimization informing development and selection of forms and behavior? It's, I wrote 2 years, but I think I understand from Mike that it's at least 3 years. So it's only in the last 3 years, with the establishment at the AA of MTech and also EDGE, that emergence has effectively been transformed from an appealing concept into a potential model for a comprehensive intellectual program for design. So it's really, really come under investigation here. It's already apparent that emergence has much to offer at both the micro and the macro level, and it's also been applied by EDGE in such a way to encourage a cross-disciplinary mode of working. And I'm not going to say anything more about MTech, because that's really Mike and Michael and Achim who'll be going into that further. But just leaving it on a looking at it in a much broader cultural model, and we start to think, what does emergence do for architecture if you're going to take even further steps back and look at it historically? I believe that emergence raises the stakes for architecture. This really hits home when I wrote the editorial for the emergence issue, and placed opposite on the editorial page, I always write the editorial on page 5, on page 4 was a frontis, which was a cross-section of a stem of a geranium. And the visual sources that architects have used over time to accompany ideas are perhaps the most telling. Whereas at the beginning of the 20th century, we were effectively circumscribing architectural ambitions by aspiring to produce buildings that were inspired by man-made technologies. So we were placing man's own inventions at the apex of innovation. And here I'm really alluding to Le Corbusier when he illustrated his books with ships, planes, cars, and they were the apex of innovation. They were what architects were seeking to aspire to. Whereas at the beginning of the 21st century, what emergence perhaps can give us is it's encouraging us to aspire to the complexity of systems and ecologies evolved in the natural world. And I'd just like to leave you with this idea. What mechanical system can, after all, compare with the reflexivity and the responsive refinement of a geranium?
Helen, thank you very much for that. My name is Jeremy Melvin. I was asked to chair this discussion and was rather flattered to be asked and accepted only with some trepidation, because where Helen, as an editor of a magazine, has edited a special issue on the subject of emergence, I have no such credentials whatsoever. And I think rather than try and give a sort of a view of what I think emergent technologies are, which I think would be trite and presumptuous, I'll just say how I came across the term, which was last year, the spring of last year, when there was an exhibition in the little gallery on the other side of the entrance hall here, to which I was very kindly invited, and I was also asked to write a review. So I had to think about what this exhibition was trying to do. And I thought there's something really quite extraordinary going on here. I'm not sure what it is. I didn't think that at the time, and I still don't know, and I may, I hope, be slightly clearer at the end of the day. But there was an enormously wide range of forms, some of them devised by students, some of them by architects and engineers working together on projects such as the Great Court just over there, or the grid shell at the Weald and Downland Museum in Sussex. Both buildings which I had already seen, but had not thought of them. I knew there was something technologically inventive about them, but I hadn't thought about any particular connections between them. And I think what this exhibition brought home to me was that there is a new way, or maybe many new ways, of looking at and exploring the whole nature of form, the nature of shape making. How can you make certain sorts of effects out of architecture? And also, how can you look at the relationships between these things? And I think one of the most memorable impressions to me of that was looking at the wonderful piece that Anish Kapoor made in the Turbine Hall at Tate Modern, obviously with support from Cecil Balmond at Arabs, called Messiahs, which you may well all have seen, probably all know of. And I hadn't thought of that as being anything more than the most extraordinary experience and commentary on that very difficult space, the Turbine Hall. And in thinking about this and being introduced to the fact that it came about, in part at least, because of an understanding of a new understanding being developed through certain sorts of new looks at geometry and technology, I thought, well, actually this is quite extraordinary because this gives the potential completely to rethink a whole series of relationships that have been taken too much for granted for far too long. The status of designers. What is the difference between sculpture and architecture and engineering? What's the difference between construction and the material technology? And perhaps what's the difference between mathematics and art? Now, all of which we have built up barriers of artificial distinction. I'm not saying that there is no distinction between them. What I'm saying is that conventions have arisen which artificially cleave them into separate things. Now, looking through the lens of emergent technologies is perhaps a way of remaking these different sensibilities in much more productive ways. I also thought that there were several questions that I, thinking as a historian rather than as a mathematician or a designer, might start to ask about the sort of things I was seeing in that exhibition. Where do these shapes come from? What are the systems? What are the processes that lead to their generation? How can we see them in relation to other sorts of ideas that are going on at the same time? And particularly, how can we understand the dynamics between different aspects of emerging technologies? These, I hope, are things to which we are not going to have answers to today, but I think we may well feel that we are at the beginning of a long and open-ended process of exploration and investigation which could go on potentially for decades. So I think, without going on any further, I'd like to introduce our first speaker, who probably needs rather less introduction than I do, Mike Weinstock, who, of course, is a well-known teacher at the AA. He runs the technology unit of the component of the graduate school. He was the founder of the Emergence and Design Group, and of course he's the assistant director of the Emergent Design and Technologies program here. Mike.
No, I'm fine. Okay, I'm just waiting for it to warm up. Okay. Now, during the course of today, you're going to hear a lot of detail about some of the things I'm going to introduce. So, the article that I'm talking about is in the first part of the magazine. And what I wanted to put forward was a series of arguments, and to use those as a way of tracing what I see as the conceptual history of emergence. Emergence came about from the intersection of several formerly quite separate disciplines, and it's very much older than people might imagine. The definitions that people use of emergence at the moment are really quite vague and not useful for us as designers, and we need to understand the characteristics of the systems from which things emerge to be very clear about what does emerge, and also we need to know how to do it. And so in this article I've tried to address both the source and the techniques. Many of the things that I introduce in that are further explained in the working practices of the 4 people that we've done extended interviews with, which you'll see on the leaflet, and I'll refer to as we go through. The first thing we have to understand about emergence comes from approximately 80 years ago. 2 founding ideas. The first from Darcy Thompson in a wonderful book called On Growth and Form, where he starts to identify the formal geometrical relations between what you might call biological objects, in this case skulls, but he studied the form of biological structures, and he found mathematical relations between them. And he used the word homologies, which means slightly different things for mathematicians as it does for biologists. For mathematicians, we're talking about the relations between forms. And he also found, he was the first to make the proposition that these things could be mathematically described. But perhaps more profoundly and more interestingly for us, when we're looking for techniques, what he said was that every living thing is a diagram of the forces that have acted on it. It gets its form through the forces that have acted on it. And he also proposed a mathematical system which those of you who come from art history might be familiar with through Duchamp, that if you can recognize in one form a deformation of another form, they are related. The second idea comes from Alfred North Whitehead, who was also a friend of Darcy Thompson. Ran into some interesting troubles at Cambridge, went, I think it was, to Harvard. He was a mathematician. At Harvard, he was appointed a chair of philosophy. And the first lecture that he ever attended on philosophy was his own opening address of philosophy to Harvard. And what he said, there are 2 thoughts there, that when unified with Darcy Thompson's mathematical descriptions, I think, and I put forward a rather longer argument for in this article, are the founding concepts of emergence. And what he said was, we shouldn't be thinking about things as objects, but they are the behavior of a process. At some level, every single object is a process. It might be very slow and it might not be visible to the eye, but everything in the world is a process. And the second thought that he puts forward is that these processes, these activities, are always interacting with each other. And that, combined with Darcy Thompson, in my view, is the founding concept of the sciences of emergence. The techniques and the instruments that we need to understand all stem from these 3 words: pattern, behavior, and self-organization. We're familiar all around us with patterns formed on the landscape. And yet, nonetheless, when we talk about pattern as architects and as artists, we still tend to think of something 2-dimensional as an arrangement of lines. But patterns in the world are produced by forces. They're produced by things and forces acting on things. This particular pattern is produced by dehiscence, that is, by its mud, and the water is gone. It shrinks. This is the most powerful mechanism in the natural world, shrinkage. And the second thought that I wanted to reinforce with this image is that patterns are dynamic. They're constantly changing. They are a reaction to stress. They are never fixed, and they're constantly under change. In kind of more contemporary AA language, they are dynamic, which is a word you've all heard a lot about. You've also heard the word complex systems, and I'm going to very briefly explain the characteristics of a complex system, and I'm going to use the most common one that we're all familiar with, which is the weather. It has only 2 components, which is water and air. It's a very important point that we understand about emergence, that at the component level, they're often extremely simple. The complexity arises, as I'm going to show, through interactions of energy. And we're familiar with the many forms that water takes. And it's quite extraordinary to think that all of these things are exactly the same component. So the form is not dependent on the nature of the component. Forms are changeable, mutable, and always a reaction to forces. Another very important characteristic is with complex systems, for example, with the boiling water, we know, you can always predict exactly at what temperature, if you know the pressure, water is going to boil at. But what you can never say is exactly where each bubble will be. So with complex systems, you can understand them at the bottom level, where the components are. You can understand the parameters of the force, and you can observe at the top level what is happening. What you can't do is predict the middle part. All complex systems are managed by energy, and I'll talk a little bit about that later. Another important characteristic is that the energy is always fluctuating. It's never constant. In terms of the weather, the Earth's orbit is slightly irregular, there's a bit of a wobble. The process itself produces kind of irregularities of energy input and output. And these fluctuations are part of the normal cycle. Sometimes the fluctuations increase, and when they reach very high levels of fluctuation, the systems collapse. Sometimes this is catastrophic, and the elements dispersed and are reorganized. So in some complex systems, the moment of the collapse is the point where the system reorganizes to a higher level of complexity. In biological systems, this is absolutely the case, that in all living things, that as through growth, many of the morphogenetic processes work on an excessive fluctuation in the moment of collapse for a higher level reorganization. Complex systems, and particularly living ones, tend to get ever more complex until they destroy themselves. Within all systems, there are patterns, and these patterns are dynamic. The most common one is the helix, which is visible in this of the hurricane last year. These are 3 successive months where we see cloud cover over the Earth. This is mapping only the water vapor, not the visible clouds. And you can see these spiral vortexes, these helices in motion. The same thing at a closer look. Clouds passing over islands, sometimes with an enormous distance between them, and you think there's, the mountaintop to the underside of the cloud is thousands of feet difference, but still that's sufficient to set off these vortex streets, which you can see more clearly here. Most of this motion comes from the rotation of the Earth. In these 3 images, if you take a ball bearing and drop it into water, as you can see on the left, it forms kind of a nice even shape, but if you twist it as you let go, it will form the spiral helix. We find the same thing now. These are images from proton accelerators, nuclear accelerators. These are photographic plates of where 2 particles collide and spin off. So even at a level below what's measurable in material, these patterns persist. And they are identical with galactic scale patterns. Similarly with this is a contemporary model of DNA. Some of you will remember the physical model of that was developed at Cambridge. We tend to think of DNA as some kind of fixed structure. The most recent paper published by the Royal Society had done a structural analysis of DNA, shows that it is constantly moving. It's constantly writhing under torsional stresses and undulating under thermal stressors. Geometry, or dynamic geometry in particular, but geometry is absolutely one of the core disciplines that we have to understand in emergence. All morphogenetic processes are organized through geometrical procedures, dynamic geometries. They control the overall patterns of growth. And in my article, I traced through Santa Fe Institute and some of the biological researchers of mathematical models. They also inform the patterns of cellular growth in human tissue and other tissue as it is forming. These two images are about, again, spiral organizations. And we can see those quite commonly occurring as a growth pattern, optimized either for sunlight in the case of the cones and flowers, or for expansion and growth in shell structures. Now, Turing, who is rightly famous as in this country as the father of computing, his real significance for emergence is his paper on morphogenesis. And what he found was a really simple mathematical way of describing how patterns emerge. And in this paper, which is, his abstraction of it, is to take two uniform colors and to mathematically describe, if you shake those up, how a pattern will emerge. Again, we tend to think of the pattern formation as we do on the top left when we do things in work in Photoshop or in Maya, whatever we're working in. But in nature, of course, they're nicely spread over, in this case, the zebra's bottom. They are formed as things grow. Patterns are not independent. They're not flat. They're not superimposed. They are part of the formation process. All living things maintain themselves through energy. And in point of fact, I think even this magnificent structure that you see in front of you, my body, 75% of the work that I do is just to maintain my temperature. It's an incredible thought. 75% of what you eat is to maintain your temperature. Only 25% of your energy input is used for thinking or running or having a shower or all the other kind of stuff. So thermal management and energy system is the majority of what living things do. Very important thought for architecture, because we normally think about energy as a kind of last applied thing that we do after we've designed something and we ask the engineer how much this is going to cost. In natural structures, the management of energy is also tied to their system for maintaining their form. That is, they can adjust their form through small energy managements. They can increase pressure in things or reduce pressure in things. And they have what I find very beautiful, but also very interesting structural strategies. When we look at a section like that, the number of functions that are in that is extraordinary. In architecture, I was trained, and most of us still find it difficult to think around this. We tend to think of one element, one function. If we want to make a facade that's intelligent and it breathes, that can manage things, current ways of thinking about it are to produce it in multiple layers, and each layer has its own function. The lesson from nature, from natural models and natural processes, is that this is not the right way to go. And I hope that in George's presentation after mine we'll talk about movement systems, and I will talk a little bit later about the management of internal economies in plants. Plants can move. They don't have any muscles. They don't have a brain. They can constantly realign themselves to the sun. Most of us have had a pot plant that slipped over and can sort of come back to the vertical again. They don't have an intelligence in the way we think of it. All of these functions are embedded in the flesh. Flesh is really, really intelligent. Plants manage two systems simultaneously for their internal regulation. The water and nutrients and so forth, and the gaseous exchange, carbon dioxide, oxygen. And it manages to do it in really, really tiny, thin things. The heating plant for this building, right, is absolutely enormous and totally inefficient. There's quite an extraordinary, if we just abstract the engineering and look at the layer of functionality that can achieve and what mechanical ventilation and plant systems in architecture can achieve, the architectural systems are thousands of times the size and tens of thousands the cost in biological terms. I think George will talk a little bit later about the movement system, but you can see on the far side again, those are the xylem tubes through which nutrients are moved up and down inside plants, and they also have a kind of helical reinforcement. This is to allow the thing to stretch and to grow. And to reinforce the point about simplicity of components, the same fibers that make my blood vessels, which are kind of going in and out like this at the moment, has the same fibers that are in my bones. There are only 4 real fiber components in the whole of the natural world. The geometry of their arrangement, how they're layered on each other, their orientation, and how they're stuck together is what produces the different performances. Again, a really critical point for us. We need to understand in these systems, if we're going to apply them, we do not need to make incredibly expensive, complex, and highly articulated components. We need to work on their interactions and their relations with each other. And you can see from any cut section through timbers, it starts off as this kind of nice perfect circle, and it's completely irregular in its form, and that shows how many adjustments it's made over the period of its life. So what we can say, and in the article I try and spell it out in more detail, is what emerges is form and behavior. And in fact, later on, we actually have difficulty when we're dealing in emergence to distinguish between form and behavior. Forms persist biologically over very long periods of time. My form is not wildly different from my parents or my grandparents, and I don't know how far back that will go. My sons are a little taller than me, but biomorphically, recognizably, still somehow related to me. Forms persist, they're never finished, they're constantly under adjustment. Whether that's a behavior of a system or a form, it really becomes a very difficult point to describe. Geometry, just to reinforce that point, happens both at a global scale, that is to do with the kind of outside of the form, but most importantly, it's constantly part of the formation processes, and it happens really right down at the very, very lowest levels. Energy systems are very critical. Feedback, in the article I've traced this first concept back to Norbert Wiener in cybernetics, the aiming of the gun, and his main argument was that aiming of a gun and biological systems are only different in degree of complexity. But feedback, I think, is he was the person to invent that term. Now, all of the terms that I've introduced to you, you're going to hear later in the presentation on evolutionary computation. Once we understand these concepts, we can put them into our mathematical and design processes. We can simulate both the characteristics of complex systems and the evolutionary processes of forms that interact with them. And we try and establish our mathematical agenda in this way. What we want to do is to produce things in an evolutionary manner. That starts to mean, first of all, things are produced in families, in generations. Most of our thinking, our best thinking, comes in deciding what to kill off. If your breeding forms, once you understand the processes and can work with it, the most difficult thing you have to do is to decide what are the parameters that are inherited. If you have a population and you're breeding a population, let's say, of laptop cases, boxes, you set up the population mathematically. You want the two best ones, or what you think of as the best ones, to combine to produce children. But if you don't kill off the rest, your population and the environment is going to take up all the resources. We need to understand two things about complexity only. There's an awful lot written about it. It makes fascinating study. But in terms of working, of inventing design processes, we need to understand the difference between differentiation and integration. And these are the two most simple definitions I can make. And in more simple terms, the processes that we need to think of and that are available to us mathematically are relations of form to pattern and pattern to form. And these are all available mathematical models. They are rarely available in engineering books. There are some. None at all in architecture. And biology is full of them. They're free, which is an amazing thing. When I got interested in this, I studied a few years ago, I found that the most generous people are mathematicians and biologists. In a way that was quite stunning to me, that in architectural circles, if I can say such a thing, proprietary secrets of process are often quite obscure, and either we're embarrassed or we don't want to tell anyone how we did it, or we want to do more of them so we don't want everyone else to do it. This kind of thinking doesn't seem to happen in mathematics particularly. And a lot of these things are instantly available to us. They're downloadable. You can email Santa Fe Institute and they will download the papers and you can make your own little mathematical models. Evolutionary algorithms have been around, I think, and commonly or publicly and freely available, I think, for about 10 years. The mathematical history is a bit longer, and I traced that out in the article. This is one of the very early ones from MIT, still available, I believe. Collective behavior, most of us have experimented at some time with kind of particles and flocks and all of those kind of things. Most biological structures are produced by thousands and thousands of extremely simple actions. This nest, in terms of thermal management, is extremely complex. And if you run that through environmental analysis softwares, the passage of heated air through this is completely organized. And yet it's produced by creatures with no brains at all. There is no plan. There are no sections. There are no lists of materials. It's just produced by iterative action. So we must understand the power of iteration. We need to be extremely simple and to set up our processes so we can repeat them thousands and maybe even millions of times. There are many other kind of lessons with this, and some of them are spelled out in the article. So I want to conclude with a small part of what we see and what I argue in the article is the contemporary agenda for utilizing emergence in architecture. Firstly, the older divisions between form and structure are meaningless in contemporary biology and utterly pointless in emergence. we need to look at the surface of things, but surfaces turn out to be structure in biology. So quite quickly we come across the difficulties of using former categories of architectural thinking. I'm going to run through a very short morphogenetic design experiment from last year, which started with a genetic algorithm developing a form. The form was moved through several different softwares and remodeled. Most of you know that difficulty when you move one object to another software and you kind of lose half the object or it doesn't form properly. But one of the interesting byproducts that came out about that is the intensity of the mesh where the curvatures are highest. And also the strands become shorter. And this starts to suggest a model of behavior which was then also researched in biological structures. And what came from that is the idea that movement can be induced into these surfaces by controlling and making very slight movements when you want to produce curvature. By moving fibers, members, very small amount, you can induce a further movement. Now, of course, this is geometrically very complex. You have to find a form of geometry for your mesh or your lattice grid where that movement will be propagated. But it is a geometrical study and not a material study. This will work in any material. It was actually built in the material polypropylene, which has almost no structural capacity at all. This is this kind of white floppy stuff that everyone chucks away when you get, and it's often used to kind of wrap up objects and things. Almost a reject material. The second important thing that was discovered in this, and developed in this process, is that forms that are produced in this way have more than one state of equilibrium. If we want to manage movement, if we want to have moving things that work in the way nature moves things, and not in the way mechanical engineering has done in the past with big levers and pistons, we have to work very locally. We have to have lots of tiny movements rather than great big ones like an aircraft carrier deck or something. But what we also have to do is manage the transition from one stable form to another. You have a material system, an arrangement of material in certain kinds of geometries. You search for two stable forms, and then you can manage the transition between them. This is a very critical point, because in mechanical engineering, where I was taught and the way most of you will have been, we manage movement by thinking where it is at the beginning and where we want it to go to, and we try and overcome the problems of accelerating the thing and then stopping it. And we use enormous amounts of energy and huge amounts of material to do it. If we follow, or try to follow, the lessons from biological systems and how they evolved their systems of movement, then we need to produce movement at a very local level. We need to manage its effects at a higher level. And they also, a great deal of that study was done physically, but in relation to a series of scriptings and digital experimentation. And they produced a control interface. And this project, they were our first graduates on the MTech program. They're now going to teaching on the ASAP program in Barcelona. And this system is under further development, and they have sponsorship and so forth for that. We have traditionally in architecture thought of form, structure, and behavior and energy all as really quite separate things. And in contemporary biology, the same image can be found that's discussing management of energy systems as when I was a child, that was explained to me the backbone of, that was what a structure was. And I was always puzzled because when I used to see the skeleton in the school classroom, it was always hung up. And if you ever like naughty children, sort of flicked it off its hook, it would just collapse. So it obviously wasn't a structure, but still it's thought of as being a structure. And in fact, the lesson from emergence and from contemporary studies, biological studies particularly, and physics, that we can regard these just as very temporary instances within a longer energy system. And this has profound implications when we think about what buildings will be and what buildings are. So there are many contemporary buildings that apply some kind of intelligence to their energy management. They are still based on what I think is a mistaken model of intelligence. They're based on remote sensing on the exterior, some sort of remote computer processing, sending signals back, and some sort of mechanical activation. Again, the lesson from evolution is that this is quite unnecessary separation. It seems to have come about because if you look at a human, they're computing bits on the top. But actually, most of our computing for environmental response happens in our flesh. You don't have to decide when you're going to sweat or when your iris is going to change. Most of your environmental systems are not computed in that way. They're computed locally in a distributed way. And we also have a very good inheritance in architecture, a little bit unfashionable now and unregarded, of form-finding experiments, which are essentially ways of stressing a material to find a stable form. The stress is gravity. It might be the stress of stretching things and collapsing them. It might be the stresses that come out on the meniscus of a liquid surface. But this is the architectural inheritance of self-organization, very rarely acknowledged. But the whole of Frei Otto's life's works, all of those experiments, are materials self-organizing under stress. And we have been researching how to extend that and also how to do it digitally. We also need to incorporate in our form-finding work structural assessment. Again, the normal process is when I was a student is that you somehow or other through some arcane process you never really told anyone, you arrived at a form and gradually you kind of worked out what its structural possibilities would be. What we've been researching and doing is that every iteration of the form-finding process can be examined structurally without us kind of taking it out and looking at it and so forth. And this is a matter of linking existing softwares, I think, and there are a great many engineering softwares that will produce structural analysis, and we can find and try to develop at the moment either scripts or connections within a software environment like Maya, ways of linking these kind of formally separate modules. We also need to incorporate in our design experiments production knowledge. This is from this year's MTech Studio. These are the drawings for the patterns on the laser cutter, which are quite counterintuitive in some way. You would never really be able to draw those in a conventional way of thinking about architecture. So if you the production system has to be part of the input into the design evolution. Not at the end, it has to come at the beginning. And later on today, you'll see an experiment that Michael and I and Achim did together where the input, the very beginning of our first design algorithm was the section of the most common steel tube. Finally, this is the frontispiece, by the way. We need to think of the surfaces and envelopes of building not as a kind of film that's wrapped around a structure, but a place where most of the functionality, the technical functionality of a building occurs. If we're going to follow the evolutionary paradigm, then we need to make very high demands of that surface. And some of the experiments we've been doing are how we can induce very small local movements which would change their angle of reflection, change the light, allow air to pass through, to be managed, then in a larger patches of that, collective intelligence would start to emerge. We need to understand that not only do buildings have to be able to intelligently manage their surfaces, their exteriority, but they need to be in communication with each other. If we could, even the most simple thing of establishing communication between buildings and transport infrastructures, which is done nowhere in the world, we would have the beginnings of what would be intelligent cities. Thank you.